All right, tonight's speaker is Dr. Mark Adams of the NRAO, and he's going to tell us about the three futures of radio astronomy. As visual or optical astronomers, we tend to kind of like put the blinkers on or the blinders on, and we sort of ignore all the high end and low end of the spectrum. But it is a continuum, and there's a lot of cool stuff out there. I will set my program aside and bring his forward. He's got a really cool graphic. There it goes. And Dr. Adams,
thank you.
The floor is yours.
Well, thank you for having me here this evening. It's a great pleasure to be here. And I'm highly impressed that you haven't blamed me for the weather, since I'm a radio astronomer. I thought for sure we would take a beating on the weather. So we're going to talk about a little bit about alphabet soup here. We're going to talk about ALMA, EVLA, and SKA. And of course, we're going to talk about what those mean. But if I wrote them all out on the first view graph, we might never get past the first view graph. But these are three futures, not just for radio astronomy, but for all of astronomy. But these are projects primarily in the radio band. And so to talk about these and to provide some context, I'll talk a little bit about the observatory today, about the NRAO, talk a little bit about what radio astronomy does and how it does it, and then talk about these three projects. So ALMA is the Atacama Large Millimeter / Submillimeter Array, so we're just going to call it ALMA from here on out. EVLA is the Expanded Very Large Array, and SKA is the Square Kilometer Array. So we'll talk about each of those after a brief introduction. This is probably familiar to many, perhaps all of you. All of the radiation that comes to us from stars and planets and galaxies and comets comes to us as part of the electromagnetic spectrum. And so throughout tonight we'll talk a little bit about parts of that electromagnetic spectrum that our eyes don't actually see. We're going to talk about radio waves. And so, let me find my pointer again. There it is. Make sure I don't zap you guys. There we go. So this little sliver in the center is meant to represent that part of the electromagnetic spectrum that our eyes detect. So blue, green, yellow, red. And blue is on this side of that little sliver, and red is on that side. And we talk about this radiation in terms of wavelength and frequency, where wavelength is literally the distance between the crest of one wave and the next wave. All of these electromagnetic waves are exactly that. We can characterize them by a wavelength, the distance between the crests, or by a frequency, how many crests pass a particular point at a given time. And waves that have long wavelength have lower frequencies, and shorter wavelengths have higher frequencies. Radio waves are out here, and the domain of radio astronomy is wavelengths of about 15 meters, about 45 feet, down to a fraction of an inch, a fraction of a millimeter, say 3/10 of a millimeter, right? There's about 25 millimeters per inch. So between this fraction of an inch and 45 feet is the wavelength domain of radio astronomy, which is an enormous piece of the electromagnetic spectrum. And in frequency, for those of you who are familiar with the radio bands, this runs from about 20 megahertz to what's called 1 T or terahertz. And 1 terahertz, a hertz just being one wave per second, is 1,000 gigahertz is 1,000,000 megahertz. So we won't get real wrapped up in the units, but if that interests you, that's how they fall out. And so I'm going to talk to you a little bit about the National Radio Astronomy Observatory today. Well, who are we? First of all, we are a national facility funded by the National Science Foundation, managed by a group called Associated Universities Incorporated. Our headquarters is here in Charlottesville, as you probably all know, right at the base of this hill. But we have telescopes all across North America, and now we're involved in a large project internationally. This is the Green Bank telescope, which is the telescope closest to us, and it represents one of the largest single dish, one big dish, radio telescopes in the world. It's a relatively new telescope. It was dedicated in the year 2000. It's located in, here's another acronym, the National Radio Quiet Zone. So a piece of our universe here on terra firma that is dedicated to minimizing the amount of extraneous radio transmissions because, as you know probably, radio astronomy detections, the radio waves that come to us from space, are in fact very, very weak. And this dish that collects the radiation is very large. It's about 2 acres of area, 100 by 110 meters. So you could fit yourself a football field right in here. And if you're standing down here, you can see here's a fence. The distance from the ground to the very top of the telescope when it's pointed straight up is about 500 feet. It's a very large telescope. It weighs 17 million pounds. It's one of the largest moving structures on land. And we actually just renovated how it rotates and made it much more robust and much more capable. This telescope is particularly good at studying things like pulsars, and we'll talk a little bit about what those are, complex molecules, including those that we believe are the precursors to life, and neutral hydrogen, the most common element in our universe. I like using the Mac because I always know how much time I have. The Very Large Array is also perhaps our most familiar telescope, primarily because of the movie Contact and Jodie Foster. Contact did a lot of good things for us, but it also made a lot of people think we listened. So sometimes when I give a talk, I include an image of Jodie at the base of the VLA, and then I put one of those red no. She's sitting there listening. You know? We don't do that. We do grow some nice flowers, though, don't we? But the Very Large Array has been in operation for quite some time, almost 3 decades, since it was dedicated in 1980. And it consists of 27 25-meter diameter antennas that are reconfigurable. That is, they can be moved around. And so the configuration that the array is in varies depending on what kind of science you want to do with the telescope. And it's been used to study all sorts of things: black holes, young stars, and planetary disks, the center of our galaxy, where we believe there's a supermassive black hole about 4 million times the mass of our sun, and cosmology, the study of the large-scale structure of the universe. Very versatile, wonderful telescope. We also operate what's called the Very Long Baseline Array, the VLBA, which is the highest resolution astronomical telescope available to any astronomer. This is a set of 10 telescopes shown here individually and in this graphic that are distributed across a very large part of the Earth. And the maximum separation from the telescope in Hawaii, atop Mauna Kea, 13,800-foot mountain, probably familiar to many of you, and the telescope in St. Croix, Virgin Islands, it's about 5,000 miles. And in between there are 8 other telescopes, and they're operated together, and they're synchronized with very accurate time signals. And all the data is brought together in Socorro, New Mexico, where we have what we call our Array Operations Center. And astronomers do really very high resolution studies of all sorts of objects, including, again, the centers of active galaxies, black holes, and microquasars. Well, you can't do any of this without some very special technology, and we're very fortunate to have within the observatory a group of enormously capable scientists and engineers who form a unit that we call the NRAO Technology Center, or the NTC, and those folks are also here in Charlottesville. So our headquarter building is at the base of O Hill here, and then down Ivy Road a little ways, we lease a couple buildings from a commercial landlord where these folks work, and they put together the technology and the signal processing equipment that allows us to push the state of the art and detect these very faint signals from space coming to us from stars and planets and galaxies. And so these folks are doing that research and development that makes this all possible. And they do it not only for us, but they also do it for the larger astronomical community. So these devices here, which are roughly that big, are amplifiers that were put into the Wilkinson, I always got to say this one slowly, Wilkinson Microwave Anisotropy Probe, or WMAP, that made maps like this lovely thing right here, basically detecting the remnant signal of the Big Bang. And that would not have been possible without these amplifiers that were made by the scientists and engineers who work for the NRAO here in Charlottesville. That group's led by John Weber. This sort of rocket engine looking thing here is a receiver. I believe that is about 45 gigahertz, a receiver for the Green Bank telescope. So these, what look like rocket nozzles, are the feed horns, the devices that accept the incoming radiation to the receiver.